Welcome to another episode of The Age of Science. In today's episode, we are going to talk about gravitational waves, how they are created, and how did we go on detecting them and how they were predicted more than almost 100 years ago with Einstein's theory of relativity. Today's guest is Dr. Marco Drago from University of Rome, and he's officially the first person who saw the first gravitational wave detection, and he works with LIGO collaboration on detecting gravitational waves. Glad to have you here, Marco. How are you doing today?
It's good. It's nice days, and okay, we are here at home because we have to stay. But yeah, it's good.
So everybody's at home. Basically, we got sick of being at home. I know that.
Yeah.
I know for physicists it wouldn't be that much of a trouble staying at home, right? There's always something to do.
Of course, a lot to do, but yeah, also some time to go out is not so bad.
Oh, yeah, I do that too, but very cautiously here in US. So let's start with an introduction, Marco. How did you get interested in physics, and what happened that you ended up doing gravitational waves, right? So
Okay, so well, I started studying physics in the high school. Yeah, as it happened in Italy. And then, yeah, I was always good in math in my life, and physics was like a step more on doing that. And I was really curious because physics explain you how nature works, the space, the universe, whatever. So you can understand. Well, you can try to understand everything to study. So there are a lot of questions that we don't have answer, but the result is to find the answer to that. So it was really my curiosity that give me the path to study physics later. And then, yeah, when I went to the university, of course, I had to decide to make my thesis a topic. And it was my chance. I would say that there was this possibility to make a thesis with gravitational wave detectors that it was near Padova, where I studied. It was the first generation detector, but maybe we will speak later about that in detail.
yeah.
And I just went there and just to listen what they were proposing to me, and then I never stopped, and I'm still here.
Ah, that's awesome. It's a very addicting field. As soon as you get into it, there's no way out. Literally, there's no way out. You're in there.
Yeah, and also, well, that time where it was very far to see gravitational wave because it was very difficult to predict when it will happen. But now that you see, it's really exciting. So yeah,
Exactly. So before getting to gravitational waves, let's go back a bit to history, right? So to
yeah,
build up to get what is actually gravitational wave, we need to start with gravity,
yeah.
right? And so what is gravity, historically speaking, right?
Well, if you want to have an historical, we have to go back to 17th century, so 1600, and to go back to Newton. So Newton was, well, I don't know, we can already say a physicist, but he was studying how the world is working. And then, so there is this legend, because we know it's not true, but that Newton was in the garden and then an apple fall down in the head. Of course, not true, but it's nice to say. And then she understood that there was the reason why the apple is falling down is the same reason why the Earth is going around the sun and the moon is going around the Earth. And this reason is what is called gravity. So gravity is just a sort of force that every object have respect to the other object just because they exist. And it's an attractive force. So the fact is that every one of us is able to attract other things according to our mass and the distance to this fact. So fortunately, we have a very small mass, so we are not really able to attract that we can see objects coming to us. But if we take the Earth that is very big, the mass is so high that the force to us is attracting, and we can stay fixed on the Earth and we don't fly away. And the same thing for the sun, that is even bigger than the Earth, is attracting all the planets and all the asteroids, and it's going on to all the universe.
So yeah, historically speaking, Newton was, I think, after Galileo Galilei was thinking about, gravity.
Oh yeah,
Yeah. And then we'll go back to Galilei because we're gonna go toward what's off with Newton's theories, right? To get to.
yeah.
but the
Well,
leg.
Galileo is important for a multiple things. One is because he created what is called the scientific method. So it's the way how we work also today. The fact that you can formulate a theory about how the world works, and then you have to demonstrate this theory is really true. It's like I can say, I may say that pigs fly, but then I have to demonstrate that pigs fly or not. So if they don't fly, I'm wrong. But if I saw a pig fly now, I am true. So I'm right. So this is the scientific method.
Yeah, exactly. Galileo started the scientific method because before him, Copernicus was talking about, hey, there's I have a theory that things go around the sun in an elliptical format, right? But he was scared to say it, right?
Yeah,
This is he just stick that this is a theory. You know, it's beautiful, but it doesn't mean it matches reality because he was scared of church. Being honest, right? But then Galileo was the only one who came and said, no, this is actually what is happening. You know, and he went that legend of standing on Pisa Tower and throwing
yeah,
rocks
exactly.
down to show. We'll get there because that experiment has something to do, right, with the fact. Now we know that the Newtonian gravity is like everybody knows what's going on with it almost in high school, right? But what is off with it? Why do we need to move beyond it and go to general theory of relativity? Somehow explain gravity that way.
Yeah, well, this is happened because, well, more or less every physics theory, we know that it can be not precise 100%. So what is happening is that in physics, we know and we have to deal with what we call the theory of errors. The fact that every time we make a measure, we try, like also our height, our weight, we are full of what is called the error. Like if we measure our height, we cannot measure precisely like a centimeter, millimeter, and also the other stuff. So at a certain time, we just stop. So some errors are not important because if I want to say I'm tall 1 meter or whatever centimeter, it's not important to say millimeter or whatever. We don't care.
Mhm.
But sometimes some errors affect how we construct the theory. And this is more or less what is happening with gravity. So we know that gravity works really well and is explained, for instance, the orbit of the planets and the gravitational, something like that. But sometimes it comes to something that is not precise. And this, for instance, what happening with the Mercury. That is the planet that is more near to the sun, the nearest planet. And what is happening, well, it's quite difficult to say, but it's that the Mercury is like it's traveling around the sun like a bit faster than what is predicted by the theory of Newton. And this is something that you have to understand why. So there are different possibilities when they discover that. For instance, the theory of Newton is maybe not precise as we think, or maybe there are some other, let's say, planet or asteroid that is perturbing the orbit or something like that. And what's happening is that Einstein, uh, after the help of also other people, of course, but he make this theory of general relativity that explain very well the solution of this problem of Mercurius and others, for instance.
Yeah, so the perihelion shift, right?
Exactly.
That Mercury's orbit looks like a flower in the long run. But theory of
Exactly.
Newton doesn't say such a thing. It's a stable one ellipse going around the sun. But the reality was different, and that's what was Einstein was working on, and ended up being correct. So let's dig into that more because Einstein built his theory based on something called space-time, right?
Yeah.
And which is, you know, the first person, I think Minkowski was the person who talked about space and time, if I'm not mistaken. But so how do we explain gravity on the nature of this space-time thing? You know, is this a real thing, or how the gravity relates to it even? How?
Yeah, we have to go back a little and speak about what is called the special relativity.
Mm-hmm.
So the fact is that actually relativity, the name, the concept of relativity was first introduced by Galileo. So Galileo was making, let's say, experiments in the ships, I was understand that if we are in a ship, now maybe we can say in a train, it's more easier for us to understand the example. If we are in a train and we don't look out on the window, and the train is not, but it's just going straight without any problem, accelerate to decelerating, we don't realize if we are moving or stop. So this is what is the concept of relativity, the fact that when an object is moving around a straight line with the velocity is constant, it's not possible to understand if it is really moving or stop, because the effect of physics is the same. So this is called the frame, what is called in physics, the frame is constant, is the same. And so what is happening is that you can, of course, relate. If you have a friend that is in the train and a friend that is outside the train, you can make fun, have entertainment. Let's say physics make entertainment like that. I don't know if it happens also for other people. But then they can make physics outside and inside the train. So for instance, we can play with a ball and measure the velocity of the ball, like that. And if they do in the train and outside the train, the velocity is different. Why? Because there is the train helping the ball to travel. So what is happening is that Galileo was making calculation about that and deriving the formula to make the relationship between the velocity calculated in the train and outside the train. But what happens instead of a ball, you use the light. So imagine you are able to measure the velocity of light, and in principle, it's possible. It's difficult because it's very fast, but it's possible. So the fact is that if you do this measure and you compare the measure in the train and outside the train, this is in constant with the formula of Galileo. The fact is that the velocity of light is everything the same, whatever you are. And this is also apparently in contact with our behaving, our feeling, because it is like it's thinking that how is possible the velocity is all the same? How is possible that the train is not pushing the light as it's pushing the ball?
Mhm.
But yeah, this is a question that is doesn't need an answer for a physicist, because this is what is happening, and then we have to take it. And the problem is that if we maintain this, we have also to modify the space and time how we think. And what is happening is that space and time are not absolute; they are relative, in the sense that the train, the distance when it's moving, like a train or a car or also a cell phone. If I move the cell phone is reducing the length when it's moving. And if I have a clock and I look at the clock that is moving the train, the clock is going slower and slower. Of course, the difference is very small, so we don't see by eye. But if we imagine to take the train going very fast near to the light, we can measure this. And this is what we have measured, and it is
Yeah.
like.
So that's where the relative sense comes, right? Because for me, sitting in a train, watching to my watch and looking at my friend's length or height, nothing changes for us because we are in that frame of reference. But as soon as we look outside of the window, if we are moving very fast, everything is going to change because you see everything going fast outside, but for them, everything is going slow, inside the train. So that's when I think the relativity comes exactly from the relative comparison. Now, you said space-time is also, relative, right? And now you talked about Galileo and, the relativity kind of between, I think Einstein was the same when he was standing in that famous elevator
Yeah, yeah.
conference, right? And then he feels trembling in his stomach and then he thinks about this, what if gravity is something related to this. Let's start from there, right? Because that will make it, and now it connects back to Galileo again. And Einstein, I think, knew very well about Galileo. Like,
Of course. Yeah, the fact is that after understanding this, Einstein make a step, another step, and say, what happened to gravity? And then he make the simple example of elevator and say, let's take an elevator that is just going up with a certain acceleration. So now we are not anymore velocity is constant, but the velocity is increasing, like when we are in a car and we are increasing the velocity of the car. So like when we are in the car, we feel that we like to stay behind because it's the car increasing our velocity. And what is happening is that we can imagine that also in an elevator, when we are in the elevator, is going up at the beginning, we feel that we are like pushing down by this acceleration going up. So Einstein saying maybe we can imagine the same thing as Galileo did, but with acceleration. So when we are accelerating up, it's not different from when we are stand up and there is gravity. So like the Earth making gravity is the same as taking an elevator and continuously accelerating up. So the two things are the same. And we are inside the elevator, we cannot distinguish which case of the two we are if we don't look around. The problem is that in this case, this means that the physics should be the same when we are stopped with gravity and we are going up without gravity. And that things make different when there is the light, because when we are going up, the light is pushed down by acceleration and is going down. And so this should happen also when we are in the gravitational field. So we are in the Earth. And this was not in the theory of Newton. So according to Newton, since the light has no masses, it's not deflected by gravity. And I say, no, it's not true. And of course, you have to demonstrate if it is true or not. But now we know that Einstein was right. And so we have to change all the way of gravity works.
So let's get a bit deeper on this, because now we know acceleration is equivalent to gravity. If you put someone in a closed box and take him outside, far from any star or any planet source of gravity, and accelerate it with g up, he's gonna think he's on Earth if he
Yeah,
doesn't know what's outside, right? Let's
yeah.
say it's a cruel experiment. The guy wasn't asleep when we took him all the way there, right? But it's the same thing. Now there's this kinds of relate to space time, right? So the sun is doing something, or Earth is doing something to space time that we feel. The gravity just kind of doesn't become a force anymore, right? If you put
Exactly, exactly. According to the vision of Einstein, the gravity is not anymore a force, and it's there is a connection between the mass and the space-time on the fact that a mass that just for being there is perturbing the space-time. It's like creating a sort of hole in the space-time that is attracting the things to going down in the hole. So the fact that we are attracted by the Earth is that it's different to imagine because we have to think quadridimensionally, as Doc say in the Back to the Future. But we have to think that we are creating a hole in the space-time and we are attracting to fall in this hole, like small or big. And then this is what is attraction, gravitational attraction is doing there. Maybe you
yes.
can imagine like in a two dimension. Imagine the space time is like a two dimension, and I wish we put the Earth in this two dimension is like creating a hole. And we are working here, we just fall down. So in two dimension, we can try to imagine and painting.
So
And
gravity basically is falling rather than being pulled, right? To it.
exactly,
So
yeah,
to make it a bit more maybe clear for our audience, we have a trampoline, and then you have a sun, right? Now I want to talk about how this translates to Earth moving around the sun, right? Because there is something going on in the curved space-time. It's not flat anymore, as you said. So
yeah,
when you put the sun in there, it makes the trampoline go down, right?
yeah.
And so what happens to Earth in this sense? Earth still wants to travel straight line, right?
Yeah, it was to travel straight, but he found that the trampoline is trying to make it falling down. So the only way to the Earth to not falling down is just to try to go around and not falling. It's
So
like when we try to make a ball in a falling stop, and if it is enough fast, it just doesn't fall down.
yeah,
That's the
those.
only way. Yeah,
So that the thing is that is the straight line for Earth in that space time,
exactly. Yeah,
right?
in the space-time perturbed, the straight line, what is called straight, is just like a circle or an ellipse or whatever it is.
Okay. So that's just for the audience to imagine that how this happens for Earth, and it doesn't because there's no friction as well for Earth to fall, right? So too
Exactly.
much.
We can imagine the same like when we are working on the Earth, we are working on a sphere. But for us, we imagine to work in a straight line, but in reality, we are doing a circle. If we imagine to do continuously and we have enough force to do.
So now this comes here that we know that the gravity is bending the space-time, right? Something is happening there, that bending. So we will get to it a bit deeper a bit later. But so now, how did this was proven? Because it's very outrageous for people who hear it the first time. What was the first proof of general relativity, basically from its predictions? Couple
I
of
would
proofs.
say that humanity was quite lucky on that because the Einstein theory of gravity is 1915. And just after 4 years after, well, actually, not, there was an eclipse of sun eclipse happening in the Earth. Now I don't remember exactly where, but it was complete sun eclipse. And there was a scientist that is called Eddington that was going to see the sun eclipse and verify this. So how he think to do that? The fact is that since the light is curved by the fact of masses, if we take, for instance, a star that we see far behind, and the star is we see the light of the stars in a straight line coming to us. But if there is something between us and the star is going through a curved path. So the fact is that at the end of the story, if we put the sun between us and the star, we see the star a little move. Not because the star is moved, but because the star has make a curved path. And for us, it seems that it's move a little because our mind doesn't think that the light is curved, but the light is straight. So the fact is that if we compare the position of the star when there is night and when there is day, in principle, we should see that they are move a little. The problem is that when there is star on the day, we don't see the stars behind. But if there is an eclipse, then the sun is there, but is not covering the stars behind. So we can just compare between night and eclipse, and we see if the stars are moved or not. And this is what Eddington prove. And actually, it's possible to find the picture of Eddington on the web, so people can just say that. And you can see that there are a little arrow to show the difference between the night and when the sun is on there. And you can see that the star are little move.
Yeah, so for people who are listening, just to think how they do that, astronomers have a map of stars when they are not behind the sun, right? So,
Exactly.
but in
Yeah.
that moment, they knew what was behind the sun, right? And that's why they could, and the angles matched exactly what Einstein was predicting. That's the phenomenal part. And the story is Eddington goes to South Africa, if I'm not mistaken. It was something like there, but either Africa. But then you go before that, there was one more trial. They were trying to catch it, but unfortunately, war broke, and the people
Oh,
who went to do that in Soviet Union were British. So
oh,
so, sorry for German. My mistake. They were German, so the war broke. They just saw them with lots of cameras, and they were like, "It's war. What are you doing here with cameras?" Right? They missed it. Right? That it would have been proven, but I think it's good that they missed it because Einstein had some mistake in his calculations. I was remembering from a book
yeah.
reading. So let's just one more question I have about this. What do you think about, is this space-time a real thing, or is it just something that we use to explain things? I'm that this has always been a
Well, no, in my opinion, it's real because it's really happening in the sense that we have a lot of proof about that. For instance, also the fact that what is called the cosmic rays, the fact that from the universe they are coming this particle to the Earth, and we can detect that. And if you see this particle, in principle, usually they have what is called a lifetime, in the sense that after some time they just in physics we say decay, outside we can say they die, to be simple, and then they generate other particles, and more or less usually this decay time is fixed, in the sense that we know that it's a little changing about particle to particle, but you can calculate statistically how much it is and make all the stuff. But this decay time is elongated for the cosmic ray because they travel so fast that they maintain themselves young, as this relativity of Einstein, they say. And so this is one proof of the fact that really this change. And then the fact that we see prove Eddington that the light is same in this curve, and there are other proofs like what is called the gravitational lensing, the fact that every planet, every star, also the galaxy, make what is called the lensing to the fact that they curve the light. So space-time is curved.
And the space-time is real. It's not something
Yeah.
imaginary, because they were thinking at the beginning in physics that space-time is just something that we invented to study matter, and matter creates a space-time. But that doesn't make sense anymore, because the new physics is saying without space-time we can't do anything anymore, right? So
Yeah. So
now we got to a point that we can talk about. So we know space-time gets curved, and when something curves you can have waves, right?
yeah.
Right. Exactly, like when you have a sheet, you can do this. That can happen to space-time. So, what are these gravitational waves per se? Like, how?
Yeah, that's another step we can go up. So we know that if we take the trampoline and we take a ball in the trampoline, it's cool. But the question is that what happens when the ball is moving? That is what is happening in the universe. And actually, if people have a sort of trampoline, they can do that because they can take a ball and just moving around. And they can see that there are a sort of waves creating the trampoline due by the fact that it's moving itself. It's like more or less when we have some water, we make fall down, and the waves are going far from when something fall down in the water. So it's more or less the same. And these are these gravitational waves. The fact is that every time we have an object that is moving, the movement should be a little complicated, in the sense that if we have just a ball rotating, this is not creating gravitational wave. If it is a perfect sphere, if you take, for instance, like a ball with some mountains or hole and it's rotating, there are gravitational waves. So it's not like everything moves is creating gravitational wave, but it should be a little complicated. But for instance, if I'm doing that, I'm creating gravitational waves. Very small, very little, we don't see that, but I'm doing that. So like we are creating gravitational wave every day for sure, and the funny thing is what is happening. So what's happened when a gravitational wave is coming? So it's like light. When light, this wave is coming, we see the light. We can also feel the light here. But what happens when a gravitational wave is coming? And that is more tricky because the gravitational wave is a wave of space-time and is perturbing the space-time. So like easily is that if we imagine the space-time, it is compressed and enlarged. So it's like as we should see ourselves, we squeeze and enlarge, we squeeze and enlarge. The effect is so small that we cannot see by eye, but this is what is really happening. And this is what was measured by the detectors.
So the gravitational waves are basically created because of perturbations or turbulence of space-time, right?
Yeah.
Something that makes the space-time like a water turbulence, exactly, when the surface, and you have two golf balls connected by a string, and you rotate them on the surface of water, they're
Yeah,
gonna give
exactly.
that's what I think all the most of the examples I've seen in the PowerPoints, that two
Yeah.
balls on the surface of the water. Now, so we don't see them because they are very weak. So in what occasions? But before doing that, just let's see when how was it predicted first? I just don't recall the prediction of them from Einstein's theory.
Well, so there was an article of Einstein in 1916, so like 1 year after, but it was quite controversial in the sense that it was clear also before that there was the possibility of gravitational wave existence, but it was really controversial between the physicists of the time. So I remind that he was writing this article explaining the theory about that. But I think it was like after 20 or 40 years later that really physicists in some congress or workshop understood and accept the idea of existence of gravitational wave as we understand now and we know they exist. But before there were a lot of discussion on how if they were real, if there were some sort of explanation, so how they were. So this was not so clear. So the article that we remind is 1916 because it's the one written by Einstein. And I think, if I'm not wrong, but I can be wrong, that at the beginning when Einstein was submitting the paper to the journal, there was a mistake. And the journal was giving back the paper to Einstein, saying there is a mistake here. And Einstein was saying, I was not sending my paper to you because correcting. This is really right. But then he understood that the mistake was there and he corrected it. So yeah.
That would be it would take a lot of courage to send back Einstein's paper and say it was it has
Yeah.
mistake, right, in 1916. I understand that. And now, like, so you said we are creating gravitational waves by our movements every day, but it's too weak because we know gravity is a weak force, right? At the end of the day, we don't create too much gravity, so our movements would give a noticeable gravitational wave. So what sources, would give us substantial energy to see these gravitational waves, right? So let's go there.
Yeah, we need objects that are really huge and really high density because also the high density is helping to make the amplitude bigger. So what is happening that we expect and we have seen for now are neutron stars and black holes. So now people have heard about the black holes and they are really becoming fancy, but in the history maybe the people don't know exactly what they are. So let's start from a star, a normal star, so like the sun, that we know. So the star, every normal star has a life time, and then at a certain time they die. So what is happening is more or less that they burn is not the real world, but they burn this internal fuel and they are creating new object and new elements. So, and they are emitting light. And then they finish the internal fuel and they collapse because the gravitational wave is, the gravitational field is making collapse. And then there are different scenarios about that. So sometimes they collapse and then they explode, sometimes not. But at the end of the story, it can happen according to the how big was the star before dying, different scenario. One of that is the neutron star. This neutron star is an object that has a really high density, really compressed. So it's like more or less the same mass of the sun or 1.5 sun, but the radius is usually more or less 10 kilometers. So it's like to take the sun and compress like big as Chicago, I don't know, or something like that.
Yeah,
So take
something.
the sun and put it on Chicago. So it's really small. And this density is so high that practically the proton and electrons are compressed and merge into neutrons. So the neutron star is practically formed by neutrons. There are also other stuff, but the big part is made of neutrons. And this is so high density that can produce a gravitational wave that we can see. And we have seen, so we are sure that.
We'll get there.
But yeah, yeah. But there are other things like black hole. So black hole is one other scenario of the death of the star. Is happening usually when the star is really big, and it's even more compressed than a neutron star. Uh, Let's make an example. If we take a black hole of 60 solar masses, or less, so 60 sun, it is its radius is like the big like Iceland. for instance,
Hmm.
if you know. So you have 60 sun in the bit of Iceland. So it's really, really complex. And so this high density and high mass create amplitude gravitational waves that is possible to detect by our instrument, but is not possible to see by eye because let's make the example. So the first gravitational wave that was detected make a perturbance in the space-time that the distance between the Earth and the Sun, that is more or less 150 million kilometers, if I'm not wrong.
Yes, exactly.
Okay. Yeah, sometimes I have to zero. It was modified by the size of an atom. So the fraction is really, 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 really small. So imagine in percentage our height, our dimension we are used to. You have to imagine that it was modified even more, even less. So something that we cannot see never by eye.
So those dense objects, basically the black holes, specifically when they form a binary object, right? If they are alone, they may not create too much of gravitational waves. But when they are in binary sense, two of them together, now put two black holes together, right?
Yeah.
And they start rotating around each other, exactly, it's like two balls on the surface of the lake, right? Creating these waves. And as they go far, you expect them to get weaker. On a
Yeah.
lake also, you don't see the waves as strong as they created in the center because of friction and other objects in the way and stuff like that. Now, so I want to talk about this. When those two black holes are rotating around each other, what happens that they start getting closer? How the gravitational wave comes out of there, out of nowhere, right? There should be a process, right?
Yeah, the fact is that already when they are rotating, they are producing gravitational wave. This is called in the scientific part in spiral phase. Why in spiral? The fact is that the gravitational wave carries energy, and this energy should come from somewhere. And this energy is subtracted to the couple that is going. So the thought that this two black holes are losing some energy producing gravitational waves makes that they approach near and dear because they need to lose the energy somewhere. So they come near and near and near. At certain time they are so near that they just collapse. There is no other way to. So they just merge in a single black hole. And when it's merged in the single black hole, the gravitational wave is even more complicated because you can imagine, well, it's difficult to imagine, but you can try to imagine that if two black holes are just merging, it's like a mess. So it's really difficult. But then when they come out, at the end of the story, it's remain one black hole. And this single black hole, even if it is rotating, is not able to produce gravitational wave because we say at the beginning that a perfect sphere cannot produce gravitational wave. But all the process can last 1,000 billion of years because depending when they start to approaching. And for now, we are just seeing the final part, just a little before when they merge and they merge. So there is, in principle, if we were able to see all the process, we can probably see a gravitational waves increasing like for millions of years. Is that our instrument for now, they are not able to see that.
Because the objects are extremely far, right? So
Yeah.
so the reason we see the closest ones because it's the most energetic part of the merger, right? It's crazy in that.
One is this, and the other is also due to the frequency because our instruments are built that they can see the particular frequency of gravitational waves near to that part of the process. So the frequency that is related to the before part for now is not in our what is called sensitivity range. So it's not possible for us to see.
Yeah, so just when Marco says, for our audience, when he says the perfect sphere cannot send any waves, this is a that has a name in physics called no hair theorem, that the black hole cannot have hair. So if you perturb a black hole, like basically shake it with an object, it's gonna become like, it's, imagine a sphere like a ball, but suddenly becomes a golf ball, like everything is, and then it releases the wave and then becomes again a sphere because it wants to go back to the perfect sphere for naturally lowest potential. Don't get to the, let's
Yeah.
not get to the nitty gritty of part of the physics, but that's why it happens. Now we know they are detected. But let's go back to what was the first experimental design, right? Who came up with this experimental design of the idea of let's go and on and detect gravitational waves? Because I think it's a very huge undertaking, right?
Yeah. Yeah, it was like in the 50s or 60s. There was Weber, a physicist, that came to an idea. And this idea was to take a bar and make this bar suspended. And the idea was that if a gravitational wave is coming, it's like exciting the bar elements and is shaking the bar, let's say easily. And he was doing that, and he was claiming to have seen a lot of gravitational waves. I think. Then other people trying to repeat these experiments, and soon after they did, and they didn't get the same results of Weber. And this was the part that they understood, that he was not really seeing gravitational wave, but maybe some noise disturbance or something like that. It's funny to say now that there is a study of building more or less the same instrument in the moon, because in the moon, according to the calculation that people made in the last year, these noise disturbances are really a lot attenuated. So it's possible to see in the moon with more or less, of course, now we are more sophisticated, but the concept of idea of Weber is possible to detect gravitational wave because you have less noise disturbance. But at that time, yeah, Earth, we are humans, forest, whatever, storms, so it's not easy to do. But this project was bring in the future years, and there were a lot of this type of instrument in the world, and they took data until like maybe 10 years ago. So until the new concept of detectors were built and were operating surely. But they were quite taking a lot of data. There were one in Italy, one or two in the US, and there were one in CERN, in Geneva, and I think also Australia. Now I don't remember all of them where they are, but they were.
So then after that we have, I think Weiss and Thorne, and they started
Yeah.
thinking about building. Uh, was 40 years ago ish, 50 years ago
Yeah, I
again,
think they
40.
started in the 80s, I
Yeah,
think.
they
Yeah, more
started
or less.
thinking about building a new detector. So what
Yeah.
is that new detector? Why it
Yeah.
is better than Weber's or even Fermi's? Because Fermi also another person who came up with a cylinder type, but
Yeah.
that wasn't also successful. So what is that makes this design more interesting?
Well, it is really a different concept. And the idea is that it's taking inspiration from an experiment that was done in the 18th century, no, 19th century. And it was the experiment of Michelson Morley. And it was used, particularly it was used to demonstrate the existence of ether. Is it ether in English? I
Yeah,
don't remember.
existence of ether. Just to
Ether.
say Einstein is almost saying Einstein is wrong again, special relativity.
Exactly. And then demonstrate the opposite, that ether doesn't exist. And the idea is the idea is simple to say, but to build is really complicated. But you take a laser beam and you split the laser beam into two orthogonal directions. And so they make the path and they go back. And when they make the path and they go back, you can combine the two light, and this is effect of the light in an interference, in the sense that there is no light anymore because the two light are combined, is they can cancel each other. And this is happening if the two light ever make the same path.
The same
And this
distance,
can the
basically, the
same
same
distance.
meters.
Exactly. But what happens when a gravitational wave is passing? Maybe we didn't say before, but the effect of enlarge and decreasing is different along the two orthogonal directions. So let's take our detector that was like that. If a gravitational wave is passing this way, this direction is restricting and the other is enlarged, and the opposite. So practically the laser beam, when it is going through the path, is making two different distances. And so when it's recombined at the beginning, it's not anymore cancelled, and you can see a bit of light. And looking at this light, you can reconstruct, let's say, reverse engineering that there was a gravitational wave passing. But
There
of
was.
course,
Go ahead, sorry.
yeah, of course, this modification is very, very little. So these interferometers, how they called, they are long 3 or 4 kilometers, and the difference of length we have to measure is smaller than an atom, and smaller than a nucleus, and smaller than an electron. So this is really something very small that you have to measure.
So this was the interferometer they thought about, and they, I think that that's the biggest national science fund, United States biggest national science foundation
I
ever
think,
spent, on
yeah,
something to
yeah,
build. And they are called LIGO, right? In a sense, Laser Interferometer Gravitational Wave
gravitational.
Observatory, right? If I'm not saying it wrong.
That's true. And actually, at more or less the same time in Europe, there were Giazzotto and Brillet that they were having the same idea, and they create what is called the Virgo. And
So what does
so,
Virgo stand for? Like for
oh, it's just remembering the Virgo cluster in the
okay.
galaxy. Okay, it's not acronym. It's just to say, oh, we will see Virgo clusters. So that's
Because
not
it
the
looks like
idea.
gravitational wave observatory at the end, right? The Virgo, right? So I was thinking maybe
Yeah,
didn't think that way back then, even when I. So,
yeah, maybe no. Yeah.
so
Yeah, and Virgo was built also. It was always a little behind because LIGO was founded by NSF. Virgo sometime need money to ask, but yeah, now it's working. They are working together since before I was started. So
So, in order to make sure that we are detecting something, because as you said, it is 1/1. Are you there, Marco? Okay, it just got a
yeah,
bit,
yeah,
yeah, slowed down for a
okay,
second. It's all good.
okay.
So let's go back to this part that in um, the gravitational waves, when we want to detect them, since they are really small, right? Like 1/1000, I don't know, size of proton. That's what is always on the PowerPoints I
Yeah,
remember we used to put. So for that, we need to make sure first there's no noise, right, from the Earth, because we live on a noisy planet. And second, we have something to compare it against to, right? Because how we will know like this is a wave that is detected. Now let's go back historically on LIGO. Well, how did you guys go on denoising these things, these gigantic 4 kilometers arms, right? Because they will catch anything.
yeah, that's a very complicated process in the sense that already the idea of having more than one interferometer and making this interferometer in different parts of the Earth is helping because it's you can make like just a coincidence between what you see between the three, and it's really improbable that let's imagine that if you have a hammer in the hand on the site and the hammer fall down on your hand, it creates a signal in the interferometer. But what is the probability that two different people or three different people in three different sides have the same hammer falling down at the same time? So this is helping a lot. But it is not enough because there are a lot of noise disturbances, and they can combine at the same time to make a sort of fake signal. So there are a lot of process to understand if what we see can be true or not. And the first check is made by a sort of control check on the electricity, on also the weather outside and whatever. There are like 200,000 checks that compare the gravitational wave is called channel, so the one that record when a gravitational wave is coming, from other channel that can record other things. So they can understand if some misbehavior is due to some electricity instability or there are some wires going some back. So there is a lot of these checks that exclude a lot of this impurity in the data and going there. And these are excluded in the beginning. But then remains a lot of other stuff that is not possible sometimes to understand, to identify. And then you use statistics. So the power of statistics that make you make a lot of calculation. So like you need, if you have only one computer, you will never make an analysis, but you need a cluster of computers to parallelize the work and understand at the end of the story if, what is the probability and the confidence that the signal that we have seen is true or not. And actually, the final answer is never 100% this is true. It's like 99.99999% it is true. So if we take the first gravitational wave detected, we measure that it can happen by chance that this type of signal is created by the two interferometers by chance at the same time, at the same shape, one time once every 200,000 years. This means that if we take data for 200,000 years, it can happen that there is a like of signal like that coming from noise. So the probability is really low, and
Yeah.
you understand that it's true.
So basically, in order to make sure I remember, when I was listening to when I was working with the success, but maybe basically collaborating with LIGO, I was remembering that they were talking all about denoising processes back then, 2014 we are talking. And like I remember there was a couple of funny stories, like about the noises. Like they had to completely get all the sewage, water system around shut up, like because it was causing vibrations. Or there was a
Yeah.
male, I think, a road that there was a big bump on it, and whenever every day at whatever time, repeatedly one mailman was passing. They were like, there's a signal here, what is this? Every day repeats at the same moment. So I remember those denoising processes. But now, so when we go to look at these detections, we need to have something to compare it against to, right? To see what does it represent. Is it a binary black hole? Is it a binary black hole neutron star? Or is it a binary neutron star? So how do we do that? Do we have anything like to compare it against?
Yeah, we have the theory that helps a lot in the sense that the process of the correlation of two objects is probably, well, it's not, it's the most known theoretical process that creates gravitational wave. And it's possible to identify because the signal is a little different if we have two black holes, if we have two neutron stars, if we have a black hole neutron star, and also according to the mass of the two black holes. So if the two black holes are very huge, it's different from they are a little smaller, or if they are different. So we have a bunch of what is called templates that according to the different masses of the two objects, they describe how the signal is behaving. And particularly, you know what you are searching for, and you try to search one of these templates in the data. And when you see that there is a matching, you can calculate the confidence of this matching is true or not. And also the fact that the black hole can rotate, they can rotate in the same way, only in the opposite way, or one can. So also this stuff can be taken account to describe as better as you can the gravitational wave. Of course, there are a lot of things that still we cannot calculate precisely. So this template cannot describe the complete possibility in the universe, but for this type of signal, they are quite good and they are used. But if you search for someone else, then it's not straightforward to have templates for everyone. For instance, a supernova explosion, you can calculate the gravitational wave coming from a supernova. There are people doing that. But for instance, since the process is really complicated, you may need like 6 months of computer calculating for one single type of supernova explosion. So it's not that you can calculate all the different parameters and all the gravitational wave constant in place. So at that time, you have to have other ways to extract the noise and hoping to see that.
Just for the audience, what Marco says, when you do gravitational wave simulations, you use clusters and extreme superclusters, not normal ones, even just for black holes that don't have any matter. Like it's just the space-time rotating around itself. And you takes weeks to get one of them, without error to merge to create a template of that different mass. Like one is twice the other one, or like they're the same mass, up, down, down. So I know there are a forest of them created just because of this, the templates. And when it goes to neutron star, it becomes even deadlier hard, because you have magnetohydrodynamics, you have to care about fluids, it just, I don't think we have enough computation power yet to get to that accuracy. Hopefully quantum computers will help, but let's see when they're gonna come.
Yeah, in that case, we are also we don't care so much in the sense that the first order is given by the mass, so you can describe quite well the waveform signature without taking account so much about that, and also the fact that the sensitivity of the detectors now maybe are not enough to see little difference of the magnetodynamic or whatever that. But in the future, with since there are in project to build a more sensitive instrument, would be possible to see the difference. So in that case, maybe I don't know what will happen before. If you build before the templates and then you find, or if you find before the data and then you maybe come back to see the difference. So who knows?
Yeah, it's always there is gonna be surprise with these things,
Of
right?
course, yeah.
So now there is just LIGO, for people who are listening, is a huge collaboration, thousands of scientists. It's not one, two, three. So it's a huge collaboration worldwide. You have Italy, Virgo, you have Louisiana site, you have Washington site, the LIGO sites. So that's the three that detected. Now let's go to one thing I want the other, regarding the noise and not noise. There's something called injection in the LIGO collaboration. So it's a hilarious. It can become very hilarious story when the injection happens. So I want to get there. What is an injection? Like, for they may hear it in news or read it somewhere. It's better to hear it from a person who works on these things and was in the process of injection. I'm sure.
Yeah, when we say the word injection, we mean that in some way we have take the data and we take one of these templates and we put this template in the data to see if we are able to get it. So there are different ways to do that. One is like a softer way. So you have just the data, the template, and you just sum the two without any problem. And this is useful because it's done a lot of way by our computer, because you have to understand how able you are to get this template or not. But there is another way, and the other way is particularly to move the mirror physically to simulate like if this waveform is really calm and maybe the movement mirrored by itself. And this way it means that when you have moved the mirror, it's not possible to subtract because it's already in the data that they come. And this is also done often because you need this for a check of the data that they come. But sometimes there are people that his job, well, one of their job is to make this injection without knowing the other people that is happening. So there are like 3 or 4 people now. I don't remember that just do it sometime and they never tell to anyone. And this happens that if you see this injection, you don't know if it is true or not, and maybe you work a lot on that. At a certain time, after months, they say, no, it was fake. We did it, it was fake. And this actually happened in 2010 when they were the first generation detector that I was there, so I remember there was this signal, and it was called the big dog signal because according to our estimation was coming to the Canis Major constellation. So Canis Major in English, big dog. And it was happening in October, if I'm not wrong. And we made the calculation, and we also wrote a paper about that. And in March, they say, no, it was a joke, it was fake. So this from outside seems really, it is hilarious, and maybe people say you are really crazy guy, and maybe it's true. But I should admit that it was really a nice exercise because after that we were more ready to a real detection. And when it was happening really in real life, we were more or less ready to what to do to the process. So it was a really good exercise. Of course, you come to the excitement and then you just fell down the excitement. But yeah,
So for listeners, when we talk about mirrors, as we talked about Michelson Morley, that you have such a thing, there is a
yeah,
mirror at the end of these two paths, and these mirrors are the ones that pick the laser back and forth.
right,
We don't want to go to details of them because they go 10,000 times back and forward to stretch the arm, right? So I
yeah.
remember that. But the sense is that that faking part, I recall I was in one of them, I think was happening 2000, was it 14, 15? Also another, a couple of these happen all the time, no? I don't
Well,
I don't remember when
yeah,
was happening one. I heard somewhere. I wasn't
two,
in there, but I was hearing in a talk that another one was happening before that. I don't know
yeah,
exactly.
it's possible now. I don't remember. Yeah, yeah, I don't remember exactly which one because
Yes.
the 2010 was the most famous for us, and then yeah, I don't remember.
They kept doing it, I think, after that. The 2010 was the most famous one, but they, as you said, they kept injecting it to
Yeah,
make sure that you
yeah.
guys are catching it. But now let's go to the night of first discovery, right? Because you were one of the people who actually, the crucial people who saw it. But since you've been in the injection as well,
Oh
so
yeah,
let's talk about exactly that night. What happened? What were you doing? Where were you at? And how was the
yeah,
feeling?
yeah. For us in Europe was near midday, and we were more or less more or less ready to have to go to lunch. Indeed, sometimes it is written there that people waiting to go to lunch they saw gravitational wave. But this is what happened is that we were taking data. Actually, we were not really at the beginning of what is called the run. So we were still in the test phase. So was not so different from the beginning of the run, but we have decided to start someday after. But the detector were operating, our algorithm were operating. And so we were analyzing the data as soon as they come, because the idea was coming since before that if you see a gravitational wave, it's possible that there are also other type of signals coming, like some light, neutrino, something like that. And the idea was that to advertise telescope as soon as possible, because if you advertise like 6 months later, they cannot point to that direction. So there was this pipeline analyzing the data, and they were sending alerts when there was a signal coming. So, at the time you were still the beginning, so you were not thinking that could really happen. So I was there in my computer, and there was the pipeline that was responsible. Of course, not only mine, but we are a group of team from Florida and Trento, Rome, Germany at the time. So there were this bunch of people working this algorithm. But I was the one that should check that it was working and make this working for this analysis. And there was this mail coming about this event. But every day there was a mail coming because it was also a way to check if it is true or if it is working or not. But then the mail was different because it was possible to see a first reconstruction of the signal. It was really nice. It was really the expected signal of a merge of two objects. And so we just saw that, and I was also in contact with a colleague in Padua, and we just saw that and say, "Wow, that's amazing!" But at the beginning, we were thinking that it was one of these Jackson. Honestly, it was so perfect, so really nice. To say, "Oh, come on, they were really able to do this injection in the proper way." But there was no database of this injection. I went to other people in Germany, in the other offices, because we were all there, and say, "Come on, there is this trigger, and do you think it's fake? Do you think so?" We had a check like 1 hour, and then we start calling people in different offices. I remind that the first guy was coming, was just knocking on the wall to the other office, say, "Come here, come here." That was, by the way. And then after an hour, we stayed at that and say, "Okay, so what do we do now? Exactly what do we have to do?" We are like, what? It was funny because we have this program with software that allow us to make online conferences that we speak every day with other people around the world. So and you can connect every time and see if there are people there. It's like a software to gamers, more or less. So you just connect, you see if there are people and you can speak. And if there are meetings, you just connect the time. And we were connecting to the operator detector to the side just to say, do you know if did you see if the detector were um, operating in a weird way? No, it's fine. Ah, okay, boom, drop down. We didn't say like we have saw something really interesting. We just, is it everything okay? Yes, fine. Boom, drop down. So they were like the why they call, bah, you know. And there was this channel to call because you can call different channel. There was the blind injection channel is called is this injection that is, and there was a guy there at the time. So we just connect and you say, "Hey, we have seen that," and the guy was saying, "What are you talking about?" But you know, we knew that he cannot say. He said, come on, we have seen that." Say, "I don't know what you're talking about. Come on." So yeah, but then we send a mail to the collaboration like there is this thing, and the rest of, so the US were starting to wake up. So there were people like waking up in the bed and looking at my mail, say, wait, what's happening?" And then going to the office. Yeah, the rest of the day was crazy because yeah, it was a bunch of a lot of mail.
I just can't imagine that blind injection guy sitting there. He's like, believe me, I didn't inject anything. You know, even if I wanna, I can't inject something that perfect. It doesn't. Wow. So, but then you went to a lot of meetings. So, what happened after? Like, you know, when everybody was, were there people questioning it, or they were just suddenly all convinced, or what happened after to make sure that?
No, it was, yeah, no, it was half and half in the sense that also, for sure, also myself, we were convinced at the beginning that it was the injection. So, in my opinion, there were two possibilities: or it was true, or it was the injection. It was not possible like fake noise because it was too perfect to be there. But yeah, true or injection, we didn't know in the beginning. But my boss in Germany, like the evening, just say tomorrow meeting at 9 to discuss this. So all the institute discussing, and I should have imagined that he knew that at that time they were not ready to make injection. So there was still something to finish. So some people knew that it was not an injection
Mm.
because we were not ready for that. But yeah, but then after some days, they clearly say it's not an injection, guys, because we were also the beginning of the run. So some people say, come on, if we have to work on a fake signal, we have also other things to check that are more important. So please, please say that. And we discovered was not an injection, and we start working a lot. I think a lot of people didn't sleep at night for months because it's so exciting and make analysis, make a lot of meeting, and I think like after 1 or 2 months, we we got the final results that it was true and the confidence, and people start to wrote the paper. And so there were some people that directly wrote the paper, and of course all the collaboration can comments can help. So imagine how many versions of the paper, how many meetings to this. And imagine that after like the 10 or 11 version, someone come, I would change the title. What? But this is science, and yeah, it
Uh,
was really harder because it was really a lot of work in that month, and it was really exciting.
I remember it was the news press, you know, what the exact year. It was 2017, right?
No,
16,
16,
16,
16 in
the
February.
exact first one, and which was actually a black hole merger, right? Not a binary. And it was surprising mass range, basically, for everybody. So, what was the mass range of these black holes?
So it was more or less around 30 plus 34 masses. Now I don't remember the exact mass, but it was near 30. And the final one was near 60. So it was not expected. So, but this is because we don't know exactly how the universe is made. And also the fact that our instrument is more sensible to black hole than neutron star. So we can see black hole really farther than neutron star. But since a neutron star can be seen by light, by telescope, we knew better what is the distribution of neutron star around us than black hole. So we were thinking that the first events we would have seen probably will be a neutron star binary, but was not.
I remember when I was doing the simulations, there were there were people who were saying, no, neutron stars are going to be detected first, and there were black hole people, no, the black holes is going to be and there were black hole neutron star people who said, no, this one is going to detect first, and then the black holes got detected first. And I remember
Yeah.
I heard it from a colleague. I'm not going to name him because it was the beginning, right? So
Yeah.
I was in another I was in my PhD doing observation, and then there was, I remember one person who was working on neutron stars. He comes and says, "What is it?" I'm like, "It's unfortunately not what you think it is." So I just passed by, like, I mean, because it was like, I mean, the I didn't know the mass range. When I heard the mass range, it was shocking. And then after that, we kept detecting, right? So it just
Yeah.
kept coming, right? How many more detected? I don't know exactly after that.
Well, now we didn't finish to analyze the last run, so we officially finished only the half. But from three, the first two and the first half of the third, we are more or less at 50 binaries. Now I don't remember the exact number, but
Whew.
more or less 50 binaries, and we are still waiting for the second part to count to make the counting. So, but it was a lot is in the third one because the first two run it was 3 months one, and the second was 11 signals. And now the third one that we increase every time we start a new run, we are improving the instrument. So it's understandable that we are increasing our number. But also during this run, there was some months that we never detect anything. And we were quite worried about that because it's still statistically possible. But we were passing from one per week. Now we were detecting one per week, and 1 month entirely with nothing. Saying, "What's happening?" But then we start again and say, "Oh, okay, that's working."
So the universe was taking a pause for you in that month,
Yeah.
not to send you any waves. But there is one specific one actually that's very interesting too. That neutron star merger, right? The first neutron star merger was crazy. At the time, I remember my advisor in PhD, he was working with the observational part, like the light from it,
Hmm.
electromagnetic waves, and there was the gravitation, but nobody knew what's going on with this neutron star merger, right? So where were you at when that neutron star got, you got the detection template? Because that's an interesting one. It caused the, I mean, all telescopes on Earth was pointing at something, and everybody was like, "Why everything is pointing in one direction?" Right?
Yeah, I can imagine. Also because it was middle of August, so I know for sure a lot of people already on vacation come back from vacation because there was this exciting thing. I was more lucky because in Germany people usually go on vacation more in July, and I also knew that I would have started a new contract in a different place in October. So I was staying in August for all the time, and I decided to go to Italy just at the end of my contract and take my vacation near to the end to make the movement more easy. So I think we were, I don't remember exactly if we were going to lunch still or what, but we were working there, and there was this guy. Maybe this can be interesting because it was a little tricky because that time, and it's written in the paper, one of the LIGO detector was having a huge disturbance, like at the same time of the signal coming. And if you see also the picture, there is you can see the signal and there is this disturbance there. So this disturbance was cut out and was not analyzed, but the other, fortunately, was analyzed. So we see the clear path in the others, and when we look at the sales, oh, come on, there is this huge glitch. So we were very fast to try to find a way to cut away the glitch, this disturbance, and then make the analysis all together and see what happened. Yeah, so we take the first hour to do the stuff, and then we we give the point into the sky and go to the partner telescope and all point into that. And yeah,
So the
so
neutron star, for people to know, the localization was also, I think, better, right? Was it the
yeah,
sense? So let's talk about localization because people don't know what does that mean when you detect something. Why do you need more than one instrument exactly to localize something on the sky? Can you talk about that, Marco? So maybe people
yeah,
are confused when you talk about it's here in the sky. How do you know it's there in the sky, right?
yeah. There are some. So an interferometer is like our air. It is not, if you just have one air, you cannot understand when the voice is coming. And the fact that you understand what is coming is get because the brain is calculating the difference when the same sound is coming to the two ears, and also the fact that the air is going this shape. When the sound is going inside the shape, it helps you to understand where it's coming from. So this is an interferometer is more or less the same. One single interferometer cannot say to you when the gravitational wave is coming from. It's not possible. But if you take two, you can make the difference between when it's coming to the first and the second, and you can understand which is the direction more or less on of the gravitational wave. And if you have even three, you can make this difference more time, and you can practically quite point out to a direction. And also the fact that since it is this shape is different when the gravitational wave is coming from this side direction or this direction. For instance, if it's coming really to this direction, you are blind because the modification is the same in the two arms and you don't see nothing. So making these two considerations together, you can try to estimate what is the direction. The first gravitational wave have only the LIGO. So if you see the estimation, the localization is like a middle of a arc of a circle, because the circle is given to the difference in time, and one middle is excluded by the fact that it's not compatible with the, the,
Mm.
the, the different time. But if you have three direction like the Newton star, there was also Virgo operating. And then it's really possible to go that. And it's like a blob in the sky for that kind that is quite small, because now we don't remember, but it was for sure smaller. So sometimes it's difficult to telescope to see all of the region in the sky because it's too bigger, too much bigger. But sometimes it's so small that they can see and find something.
Yeah, I remember that one specifically because like every telescope was pointing at an NGC and everyone is like, what's going on? Like I was doing observational astronomy and my job was also doing observations, and I'm hearing from different people that the telescopes are pointing at something, and I'm like, why they're pointing at that thing? And every single of them are pointing at that thing, different wavelengths. And then it comes out this was the neutron star merger, which I think was the longest I think the craziest observation ever made, I would say, in observational astronomy as well, because so many telescopes looked at
Yeah.
it, plus the gravitational wave. I think it's a very complete picture. It has been helping a lot. Hopefully it will increase, because it's the neutron stars are very interesting. They'll give you
Yeah.
light as well. Any detection on neutron star black hole merger yet?
Yeah, they have been in the last run,
Mm.
but I don't remember how many now. I know.
We went from nothing from
Yeah.
2014 to now you don't remember how many there is of one type. So that's a
Yeah.
huge advancement for people to know. So let's now they are detected. There is interest. Everybody wants to build their own detector almost, I've heard. But there is a detector in Japan coming on, right? Kagra. I remember when I was there, I was in the team, I was listening to Kagra's build. It was crazy. Like they were building it in a mountain. Like,
Yeah,
yeah,
the other in the mountain inside. Well, there was a previous instrument there, and they are building that. They start take data in the last year. It's still
really.
at the beginning. Yeah, they just make operational to see it work. Still, the sensitivity is quite low to make science, but they already start taking data, and their plan is to join the next run. Now it's difficult also with COVID understanding when we start because there was a plan that is
Shifting.
going further and shifting. But their plan is to join in the next run. And if we have four, the battle would be really interesting. And also there is the plan like India, in
Mhm.
India, like one. But then I don't know exactly when it will be because,
Yeah, that is that's gonna be interesting if you have five of them. Then the localization is gonna be insanely accurate compared to
yeah.
what we have right now. Um, Now let's talk about one more thing. Get to the so we have gravitational waves. What kind of science we can get out of it? Like what is it gonna come out of it? Because is it like a new like first we saw electromagnetic waves. We didn't know what's gonna come after, right? Are we in there? Like, is it something crazy waiting at the end of the door?
So it's a yes and a no. So if we take the binary neutron star, it's really exciting because from only that detection we got already new discoveries. For instance, one is the calculation of the gravitational wave velocity is pretty accurate, thanks also to the fact that you see the light. And it's the confidence of the gravitational wave velocity is the same of the light is really accurate with that event. You can do also without with only a binary black hole gravitational wave, but this is helping a lot. But the most outstanding fact is that we can, since we saw also the process of the merging of neutron star with the light, also, we understood that the production of heavy metal in the universe is made by merging of neutron star. So there were theory about that of calculation that the theorists already made it, but we never saw before. So this was a confirmation and was something that was quite new because it was it's still probably also a doubt on where the heavy metal in the universe are produced because supernova can produce, but according to our calculation, it seems they are not enough to explain also our Earth. So so merging neutron star is a possibility. So at that time, it was really a huge discovery. Now there are still people making calculations. Sometimes there are new papers that say we are not sure that is enough. So maybe there is something other process. So the debate is still open. But it was a really astonishing discovery at that time, and it's still one of them. If we go to black hole, the science could be really exciting because it's the first time that we can try to study black hole particularly directly, in the sense that we can stress the system of gravity in a very strong regime, is called. So there is no other way to, for now, to study black hole at that level. The problem is that up to now, nothing exciting come out. So it would be also nice to see like some deviation from Einstein theory, like some small things that Einstein theory is a little wrong. Nothing for now. It's binary black hole are described perfectly by the Einstein theory. There is no modification for now, and so we can make study of population. We can study if there are alternative theory of gravity, if there are something wrong. For now, nothing come out. We hope future will be. Yeah, I don't know.
We hope something anomaly. It's exactly
Yeah,
like the LHC, right? When they discovered Higgs, everybody was like crossing fingers, please, Higgs don't come out. Let's just
yeah,
something else comes out so we can find a way to break through this barrier that we are facing. Physics is in a very not it's both nice and scary place right now. Everything is coming as predicted and nothing goes broken, so we can come and say, hey, we can you know we need to build something new at theoretical. There's one thing. I was talking to Peter Voigt last episode.
mhm,
The problem is like also there are no journals letting people publish if they have a wrong anomaly,
uh, okay.
right? If you have a wrong anomaly, they're not going to let you publish that, right? Maybe there is something in that wrong anomaly, but you don't see that. There is something, but there's no way to do that. So also, I know there is Lisa project,
Yeah,
right? to, because as you said, the frequencies for us on Earth is different than Lisa. Why is that? What, how is Lisa gonna be like exactly outside?
Well, so things can change because the first project is different from the project now, but the concept of LISA is the same of interferometers, but they will be sent to space. So first difference that is quite important because there is no noise coming from human or something like that. And also, since you in space you have a lot of space, you can say that the arm's length will be millions of kilometers. So in this sense, it's completely different the things that you can say because the frequency range is very, very, very low. So it's less than the hertz. So it's
Uh,
possible to see, for instance, quite a long part in the binary collection, and you can see also probably white dwarf, right,
yeah.
or something like that. So the physics can be really different. You can also try to complement because maybe the same signal can see in different time in Lisa and on the Earth because they come to frequency at different time. But for sure, it's one of the most astonishing project because you have to send to space something that should be really precise to maintain in the orbit and even little difference should be checked. So it's really a big project. But so I don't know. For now, it seems to come out in 2034.
Ooh, okay.
But yeah, it's not. Of course, it's difficult to predict because space missions are difficult. But there was Lisa Pathfinder that went to space around more or less in the time of the first detection, and there was a prototype that it was only one arm, so was just a testing. You cannot make science with that, but it was testing if you are able to get the sensitivity you want. And the astonishing part is that he got better than expected.
Oh,
So
okay.
really a huge better. So already for now that you're not in the final stage, you got a better sensitivity that when you are expected. So who knows what will happen then when you feel go to work.
Maybe they will accelerate the Lisa project, hopefully, to do some.
Maybe, yeah, who knows. There
Uh,
are also other projects in the Earth like Einstein's telescope and oh now we have. So there are other interferometers that will be bigger. So and so also that will be higher sensitivity. Also the infrastructure will be different. So there is the third generation that is already planned. Of course, it's still in project, so we still don't know exactly where, but it's another thing that will improve a lot.
how does it look like, the newer version? Is it going to be the same concept of two arms or?
It's so it depends in the sense that the Einstein telescope seems for now that should be like a triangle like Lisa, but it's not really decided yet in the sense that it's also possible that instead of having one telescope as a triangle, maybe you build two L in two different places.
The,
So if
the triangle is because if it's coming this way, not this way, it still gets detected, right? Because you have a triangle anymore.
yeah, and then you like if you have a triangle, you have three interferometers that are not uh, uh, all independent because the third one is more or less a combination of the other two. But it's still an advantage because the noise same different. So it's still something that you can get an advantage. And of course, if you have the triangle, you can try to see all the sky. Yeah.
So, what does the future look like for, in your mind, for gravitational wave? Like, where are we going?
The future is bright, even if we don't see it's bright. No, it's for sure exciting because now that we know we can see them, and we have also an idea what we are seeing, where we can improve. For sure, uh, we can expect a lot of science about that. I hope that maybe not the second generation, but you never know because even from the binary neutron star, you got a lot of science. Maybe you have also something new that you don't expect. We are all waiting for the supernova to come out in the next years. hope the universe is helping us in that. But I expect that maybe in 5, 6, 10 years there will be really a lot of science really
Uh,
changing maybe our idea of universe. But yeah,
my case is I'm really hopeful that gravitational waves will give us some understanding of the space-time's nature itself, right? Because it's coming from space-time's extreme behaviors in a black hole specifically.
yeah.
It would be nice to see what's happening there, but I know it needs a lot more data points for that. So what, since we are getting to the end of the podcast, I just want to ask you two more questions. What is your advice for people who are planning to become physicists, specifically going for gravitational waves? Like maybe they are in high school or under college right now, and they are hearing this and they want to say, "We want to do this." How would you? What would be your suggestions to them?
Oh well. Well, I think maybe it's in the sense it's something that you will maybe decide in the university part, in the sense that maybe it's possible that you can decide to study physics or also engineering, because also engineering help a lot on building the stuff, and then you can go to gravitational wave. Maybe it's too early to decide if you are not in the university to go really there, because maybe you can understand also when you study university, like physics is the one that I know, so I explain that you know a lot of other stuff, and maybe you encounter something that you really interested in more. So first come to physics, and then understand if you really want to do that. And then there are a lot of places in the world when they work in a way, so you can just get informed in the one what they work and what you are more interested in, and then just go there. And there is a lot of work to do, so you are always accepted to help and to contribute, and there are a lot of science that you can do even when you start, because when you start with a PhD or also undergraduate thesis, you have your project, and it's important to do, and you grow up. So first of all, it's better to decide what you want to do in your life more general. If you like physics, engineering, math, or if you like something else, that's fine. And then if you understand that it's your path, just go. The doors are open to everyone.
Mm. This is a question I ask everyone. The last question for everybody is, what was the book, the most favorite book that you read? And when you finished, you went, wow, what was this? So everybody has such a book usually in their lifetime.
Well, in physics or
In
whatever.
general, whatever book that really caught you.
Oh, well, maybe I think I like that particular book of Agatha Christie. I'm 10 Little Indians. I think it's the right
Maybe you can write
title.
Tale of Little Indians,
10 Little Indians.
10 Little Indians.
Yeah.
I'll write.
It's I admit that Agatha Christie is really difficult in the sense that I like to read and understand, but it's really impossible to me to understand who is the guilty one. So, but at some time I'm really pissed off because say, come on, that's not it's too difficult. You cannot. It's not possible. But that one is really, I don't know. It's at the end of the story you say I would never guess it, but it's really well done, and it's also small because it's really not so many pages. But it's the story is simple. There are 10 people invited to go in Iceland, and each one of them are killed in series, and you don't know what hell is happened because they are the only one. You don't know if there's another one killing them. You don't know if one of them is killing the other. You just what? And this short story they say about these people that die one by one in different way, and the people that die in the novel they died in the same way, so they already knew how you will die, but you don't know who will be.
Okay, that's an interesting book. I'll put the link down there. Um, Thank you for being here, Marco. Appreciate your time.
Thank
Hopefully, we
you
can
for
have
the
you back again.
Thank you for the invitation.
Okay, I'll stop here. That was a good run. I
Oh
hope I didn't
well,
give you a hard time with questions.
Oh, no, no, very good question. No, no. Sometimes you just, while you are explaining, you say, come on, I'm not saying that I should say better, but yeah,
It
okay.
happens, right? It's just that
Yeah,
more natural, the better. I wanted first to send you questions, but usually I don't do that because what happens, it makes it much more conversation based.
yeah. No,
When
no,
you
I
send,
understand.
I started with sending questions the first episode, and I saw it becomes more scripted. But then when you don't have it,
Yeah,
just changes avenues. It becomes more interesting. For also, you can decide what you want to talk about suddenly, right? That's a better thing. So you're now in the University of Rome,
yeah,
Marco,
yeah, yeah.
doing. Are you assistant professor now?
Yeah, actually, yes. And
Congratulations.
thank you. Now, yeah, in 1 month, I will start the lesson, and it's the first time that I will teach 90 hours in a semester. So it's, yeah,
90 hours you want to teach?
I am. Yeah, yeah.
Oh, you've
Yeah,
been
it's
researcher for past 8 years, maybe, right?
yeah. I was like when I was before, I was giving lesson to PhD, so it was like 20 hours, 10 hours was really slow. And also
Uh,
there were like two maximum people at the one courses, so it was really more colloquial. Like, yeah, we are me and you, we know, yeah, this is the fact. But now I still don't know how many students we have, and yeah, 90 hours. So
90 hours. That's a lot of teaching. I left after PhD, so I'm outside now, working in industry.
I would honestly have choose only researcher path if I could, without teaching too much. But yeah, you cannot decide all the time.
No,
So
that's the reason I came to industry is I'm not gonna be worried about teaching too much in industrial world. I can just do research and
yeah,
create products, right, based on the physics. I wished I could stay in academia, but it didn't happen. It's harder in US sometimes to stay in. It's much more competitive to get into assistant professorship here.
yeah, I can imagine. And it's
400.
also difficult to remain in the sense that it's yeah. In Italy, I would say when you are a professor, it's done.
That's good.
It's like if you do, you have to teach because you are forced. But if you don't do so much research, it's not that someone kick you out.
Yeah, it's here. It is different. I remember
Yeah.
when there was a position open. There were like 450 applicants.
Wow.
450 applicants for one position. You just feel like, what is my luck next? How many postdocs am I going to go? 5, 4 till somebody opens a position that they'll accept me, right?
My God.
Yeah,
I
it
didn't
is.
know that.
It's getting tougher and tougher because people don't get retire.
Yeah.
They
Yeah.
just sit in their
Yeah.
chair longer than they should. It makes it harder.
But here in Italy, even when you are retired, sometimes you remain in the university. I don't know if it happens also there.
I
You
mean,
are officially retired, but you can stay 1 or 2 more years. Yeah.
yeah, but I'm just saying they should say this chair is open now for somebody else, right? So to come in,
Yes.
you're still emeritus professor, but that needs to be filled. But that doesn't happen in US too often.
Mm.
Yeah, it's all good. I still do physics at my spare time,
Yeah.
but I do. I'm trying to mix AI with physics a lot. So that's what I've been doing. Trying to find a way to use AI to create explainable physics. Kind
Oh.
of force AI to find something that we can't and try to use it to find a way to give us an access to what he sees or what it sees to give explanation. So it's going to become a tool. That's what I'm trying to do. Like I've been working on it for past 2 years now. I don't know if it's going to end up being done by next 3 years, but whenever it is done, right? It's the first thing is the big thing if it works.
Yeah. Sure.
Yeah,
Ah,
because
interesting.
it will become like this. It will give you give it images, it learns what is it looking at, right? And then you create a backward engine that goes to
Mm-hmm.
this AI and creates features in a reasonable, physical, understandable images or anything that you can look at and say, because of this he saw that, but I've never seen this before.
Ah,
Uh,
oh.
that's what I'm doing. Yes, hopefully that works. LIGO can help use it too, right? That's just
Oh, for sure. For
they're
sure.
using it already. I know machine learning is heavily used in LIGO, but this is like more general idea than that. I'm working more on turbulence side, fluid dynamics part, just to see if I can make that work with AI. I don't know.
Well, if it works, let me know.
Oh, sure, definitely. Sure. I have already one working scenario, right? But
Oh,
it is not enough. One working scenario. I'm working on pendulum, right? Simple. So like
okay.
get a simple harmonic oscillator, make a machine learning model to simulate this, understand it basically, the physics without knowing the physics. And then try to relate this to the phase space behavior of the
Uh-huh.
and see if it sees the phase space.
Ah,
So that's what I'm trying. It's still in the baby steps, but that's the beginning. And if you can make that work, any other system has a phase space behavior. So,
sure.
and the AI can see that because it's much more nonlinear than any other thing we've ever known as humans. It's interesting. I highly recommend you to check AI as well. I'm sure you're using it for your work.
Yeah, neural network. We are. I honestly quite ignorant about that, but we are people that are really using very strongly. Uh, I am approaching that. So, but we are doing that. Yeah, AI not now, but yeah, why not?
My PhD's, I think half of it I was working on AI and
Hmm.
mixing it with astronomy observation. And it worked. A couple of times it worked phenomenally because I was not expecting it to work. But there is a book if you are interested for people who want to start using it.
Uh-huh.
I used that book as graduate school textbook. What was it called? It's called Deep Learning. That's it, by Ian
Ah,
Goodfellow. It's available online by him in a website. You can just click on the chapters and read them. After reading that, you're good because as a physicist, the mathematics of it is joke because the math is very easy there. It's just derivative and statistics, and you're like, I know all of these things. What is the intuition? I think if you read that, it's gonna give you a lot of crazy ideas for using it in gravitational levitation.
cool.
Let me know if you one day you want to collaborate on something on using AI and gravitational wave. I am always open to use AI for anything.
But if it's everything that works is useful, so why not? Yeah.
Sure. Thank you, Marco. I don't want to take your time. I know it's like 5 p.m. right now there, 6 p.m.
Five. It's in five.
It's dinner.
And since it's not raining, maybe a little work I can do outside.
And it's dinner time, right? So go ahead.
Ah, no. Here dinner is after 8. Come on.
My dad used to study in Milan Polytechnic,
Ooh.
there, electrical engineering, 70s ish, 1970s, I remember. Um, he was very like Italian, like,
Ah,
type of person. I really wanna come to Italy, but I was gonna come, but COVID came, and I'm like,
well, yeah. I know. I hope it will be solved soon so we can travel again.
yeah, I definitely wanna come to Italy and visit Florence and Rome and all. I have friends there, but never seen them. So
Oh.
uh,
It's good to have friends everywhere, so you can just go and yeah.
yeah, hopefully I'll come and visit you there when I come to Rome.
Rome is big. There are a lot of things to see, so I still don't know how many there are because it's a lot.
Whenever you came to US, let me know. Like you're gonna definitely come after the COVID ends, right? So
Yeah, usually we have one meeting in US per year at least with the LIGO
well,
collaboration. So
I remember there's one big one, Pacific Gravity meeting also is huge. That's for more theoretical people, right? In San
yeah,
Diego or
yeah,
okay, I'm not gonna take up more of your time, Marco. Hopefully I can have you back later for one more. Have
yeah. Who knows? Why not? See
a
you.
great
Thanks.
night. Ciao.
Ciao.
Bye.